Welcome to the third video in a 5-video series on algebra basics, Exponents. Here's an example of an expression that has an exponent. This is pronounced 3 to the 5th power, or 3 to the 5th. The 3 is called the base, and the smaller raised up 5 is called the exponent. And what this represents is the base being multiplied by itself 5 times because we're raising it to the 5th power. So this is the expansion of 3 to the 5th, and now I have to multiply all these 3's together to find a simplified answer. When we multiply things, we multiply them in pairs. So the first two, 3 times 3 is 9. Then taking the first two of that expression, 9 times 3 is 27. Again, simplifying further by taking the first two, 27 times 3 happens to be 81, by the way. And not that you would have that memorized, but 81 times 3 finally is 243, which is the simplified version of 3 to the 5th power. So let's examine what happens when we have an exponent that's 0. For example, 2 raised to the 0 power. Well, the short version of this problem is the answer is 1. It turns out mathematicians decided that anything to the 0 power should be 1, except for 0 to the 0, which is an exception for later. But why did mathematicians decide that anything to the 0 should be 1? Here was their logic. Let's look at powers of 2. 2 to the 3rd power works out to be 8, because it's 2 times 2 times 2. Well, what happens when I decrease the power by 1? 2 times 2 is 4, and if I decrease the power by 1 again, 2 to the 1st power, or anything to the 1st power, is itself. And one thing you'll notice here, if you compare these columns, is that on the left side, the exponent is decreasing. And on the right side, the results are being cut in half each time. Half of 8 is 4, and half of 4 is 2. Mathematicians decided to continue this pattern, that if we decrease the exponent by 1 more and brought it down to 0, that the answer shouldn't be 0, that it should be half of the previous answer. In this case, 1. Now, that's the reasoning behind the mathematician's logic. If that reasoning escapes you, please just remember, anything to the 0 power is 1. Let's go a step further into negative exponents. Suppose we were trying to do 2 to the negative 3rd power. Well, it turns out mathematicians decided that the result here should be 1/8. Strange answer. Let me explain their logic. Again, looking at powers of 2 and decreasing those powers, one notices, just as we did on the previous slide, that every time you decrease the exponent by 1 degree, that the answer gets cut in half, so to speak. Again, that was their logic behind 2 to the 0 should be 1. But shouldn't this same logic, if we want a consistent mathematical system, shouldn't it continue? If I decrease the exponent by 1 again, bringing it down to -1, then I should have half of my previous answer. Well, half of 1 is a half. And by the same logic, if I decrease the exponent by 1 again to -2, I should have half of my previous answer, half of a half being 1/4. And if I decrease my exponent by 1 again, bringing it to -3, then my result should be half of the previous result, or half of 1/4, which is 1/8. And this is the logic that mathematicians used when they decided how to deal with negative exponents. Now, that logic isn't for everybody. Some people are more mechanical in their approach to things, and if that's you, you might find the following explanation better. Let's start this problem over. Suppose you're asked 2 to the -3. Here's one way you can handle a negative exponent. See the negative sign there? Pretend it isn't there. For now, anyways. Just do 2 to the 3rd, meaning 2 times 2 times 2, which as you can see works out to 8. But then tell yourself, oh wait, I had a negative exponent. I wasn't actually working out 2 to the third. I was working out 2 to the negative third. Well, now that you've worked out 2 to the positive 3, which is 8, just take the reciprocal of that, or 1/8. It's a nice mechanical way to deal with a negative exponent. Regardless of how you arrive at it, here's something worth noting. Even though the exponent is negative, the result is positive. So when we raise a base to a negative power, we get a small positive answer. Well, now that we just looked at what happens when the exponent is negative, let's compare that to what happens when the base is negative, such as negative 3 to the 4th power or negative 3 to the 5th power. In the first case, we have an even exponent, and in the second case we have an odd exponent, and we'll see how that does play out a little differently in each case. First, the even exponent. Negative 3 to the 4th means this by definition: 4 factors of negative 3 multiplied. Remember, when we multiply, we can only multiply in pairs, so multiplying the first two, negative 3 times negative 3 is positive 9. Then multiplying the first two of this line, positive 9 times negative 3 is negative 27. And lastly, again, a negative times a negative is a positive. 27 times 3, by the way, is 81. Again, not that you would have that memorized. Let's compare that result to the odd power of a negative base. Here's what negative 3 to the 5th means by definition. Again, multiplying the first two give positive 9. Then multiplying the first two of that result gives negative 27. And when we continue here, we end up with a positive times a negative, which is a negative. The one thing that we can say happened in this case is that when we raised a negative base to an even power, we got a positive answer. But when we raised a negative base to an odd power, we got a negative answer. That result, by the way, didn't just happen in this one case by accident. That result is generalizable anytime you raise a negative base to an odd or even power. So now that we've seen what exponent problems look like when the base is negative, there is one thing that I have to warn you about. Let's compare this problem that we just looked at to this one. The first problem, the base is negative 3. Here, as we saw a minute ago, they're asking us to raise negative 3 to the 4th power, meaning I have 4 factors of negative 3 and a result of positive 81, as we already saw. The problem on the right, however, despite the fact that it looks like the base is negative 3, when a mathematician writes that expression, they're not including the negative sign in the base. They're effectively saying, just raise the 3 to the 4th power, and the negative in front means to then take the opposite of that result. So raising only 3 to the 4th power gives us positive 81, and then taking the opposite of that gives us negative 81. Here's a different way to look at the same thing. When we see a negative in front of a base underneath an exponent, do not include the negative as part of the base unless there are parentheses, which in this case there are not. Think of it instead as negative 1 times 3 to the 4th. I realize there was no 1 written there, but that's the interpretation that we should take. And we'll talk more about this in our next video, which covers the order of operations. But working out 3 to the 4th power gives us 81, and then multiplying by negative 1 gives us a negative. And while this may seem counterintuitive, there's one thing that we should keep in mind. As mathematicians, we get to decide what our symbols mean. If we decide that putting a negative in front of the 3 means that it's part of the base, which we haven't decided, then that could be our rule. But centuries of tradition, for whatever reason, mathematicians have accepted that When we write a negative in front of a base and there are no parentheses, then we're not including that negative as part of the base. So when you see this problem and you think, I'm raising negative 3 to the 4th power, you're not. You're raising 3 to the 4th power because that's what the mathematician who wrote it intended. And that completes the third of this 5-video series.